In this video, we are going to look at atomic orbitals and electron configurations. So we need to figure out where electrons are hanging out in atoms. We cannot know where an electron really is within an atom. So what that means is we can't know both the energy and the location of an atom at the same time within, or sorry, we can't know the location and energy of an electron at the same time within an atom. So what we do is we use kind of like a density map to identify where the electron is most likely to be found within an atom. So here is an example of a density map. We have the Springfield Police Department 4-week robbery. And each one of these instances is going to correspond to some sort of crime. And we can see they're kind of spread out over here. Over here, we have some over here, but there's a high density of robberies right here in the middle. The same is true with electrons. We use the Heisenberg uncertainty principle to do a ton of calculations, identify where it is possible to have an electron, and those calculations give way to a shape. And these shapes are called orbitals. So an orbital is a three-dimensional region that is the most possibility of where an electron is. It has the highest probability of where an electron can be. So, for example, here are all those little calculations that resulted in a ton of little dots. And here we have a lot of electron density. And then as we move out further, they get spread out farther and farther. The same is true right here. And from these, we get these different shapes. We have four different types of orbitals. The first is the s orbital, and it is spherical in shape and contains one suborbital. A suborbital is just a smaller orbital. So all of these different orbitals are going to contain these suborbitals. Now, the p orbital is the next one. It has more of a figure-8 shape or a dumbbell shape. Sometimes you'll hear it referred to as a peanut shape. And the p orbital contains three suborbitals. Those suborbitals are shown here. So here we have kind of our dumbbell shape. Notice there's no electron density in the middle. Now, these shapes can be along the different axes. So here we have it along the here we have the p orbital along the y. Here we have it along the x, and then finally we have it in the direction along the z. So we have three suborbitals. Now, we are going to primarily focus on the s and the p orbital for this class, but we also have a d orbital and we have an f orbital. Now, what's super cool is we have a theoretical g orbital. So if more elements are discovered, they will use the g orbitals. Now, something you need to be aware of is two electrons can fit into each orbital. So if we have something like the s orbital, there's only one suborbital, we can fit two electrons. In the p orbital, since I have 3 suborbitals and 2 can go into each one of those suborbitals, then I can fit 6 electrons. The d orbital has 5 suborbitals for a total of 10 electrons, and the f orbital has 7 suborbitals for a total of 14 electrons. But like I said, we're primarily going to focus on the s and the p orbitals for this class. Now, the electron configuration of an element The electron configuration of an element is a way to show where those electrons are hanging out, which orbitals those electrons are hanging out in. Now, if we look at the electrons in beryllium, Be, beryllium has an atomic number of 4, so it means there are 4 protons. It is charge neutral, so how many electrons does it have to have? Exactly. It has to have 4 electrons as well. Now, those electrons are going to exist in very specific places. So, this one out in front is going to talk about the energy level that the orbital is in. And then we have our orbital, which orbital it's in. And then this number up here is the number of electrons. So, beryllium has 4 total electrons. So I'm going to put them in the lowest energy level first, which is 1, and then the lowest energy orbital, which is s. And remember, we can only fit 2 electrons in the s orbital. Now I can go to the next energy level. In the first energy level, we only have room for 1 s orbital. In the second energy level, we have more orbitals available. But since beryllium only has 4 electrons, I only need to use 2s2. Now, we are only doing simple electron configurations for this class. I only expect you to know the full electron configurations for elements 1 through 18. And then for the S block elements, which we'll talk about in just a second, you do need to know the noble gas configurations of those, but only the noble gas configurations. So, what do I mean by S block? The periodic table is divided up into these different blocks, which describe the type of orbitals those block use. So we have the S block right here, which uses the S block, or which uses the S orbital. The P block is over here, and it uses the P orbital. The D block is in the middle, and the F block is down here. Now, remember, we can only fit 2 electrons in our s orbitals. So that's why here we have the s block. I can fit 1, 2 electrons in it. Go over to the p block. 1, 2, 3, 4, 5, 6. There are 6 groups in the p block. I can fit 6 electrons in it. So when you are filling electrons in, you're going to use these numbers here as the energy levels. Most of the time with your periodic tables, they will be written along the side. If they aren't, you can just write them in. And then you will start filling in your electrons for your electron configurations by atomic number, which is equal to the number of electrons in charge neutral elements. So I will start at hydrogen because it has 1 electron, and I can go across the periodic table until I get to my desired element. All right, when you are doing these electron configurations, sometimes it can get really long. So we have what is called the noble gas configuration, or sometimes it might be referred to the noble gas shorthand. When you are doing this, remember a single orbital can contain a maximum of 2 electrons. And when you are filling electrons in, The S is usually first and then the P within any energy level. We will not use the D or F orbitals for this class. So when you're trying to use the noble gas for shorthand, you want to select the previous noble gas, and that will stand for all of the electrons in the core of the atom. You want to begin the configuration with the noble gas symbol, and it's always listed in brackets. And then continue with the s orbital in the row in which your element can be found. So everybody find magnesium on their periodic table. What is the atomic number of magnesium? Yes, it is 12. So magnesium has 12 protons, which means it must have 12 electrons since it is charge neutral. So let's see where those electrons hang out. We'll go back to our previous slide with our periodic table. So magnesium, go ahead and find magnesium on your periodic table and write it in on the periodic table that we're using here. Yes, magnesium goes right here. So when I'm filling in my electrons, I'm going to start where hydrogen hangs out. Notice this is in the first energy level. So I'm going to write it as 1s2. And the thing that is a little fun about this is here's my first electron with hydrogen, but my other electron is with helium way over here. That's the only part of the S block that does that. Now I can go to the second energy level. So I'm going to fill in the S block first. So it will be 2s2. And then I'm going to go all the way over to the P block. So we'll go all the way over here and fill in these P electrons right here. So this is going to be still in the second energy level. Now we're in the P block though. So we're using the P orbitals. 2p6. Notice when I'm filling in my electrons, 1, 2, 3, 4, 5, 6. I have a total of 6 electrons that can fit across the p block. Now, if we stopped here, I have 2 electrons here, 2 electrons here, and 6 electrons here. So if we added all of these up together, it would be 10. Well, what do you notice? Neon is right here. It is a noble gas and it has 10 electrons. So now I don't want neon, so I'm going to go down to my third energy level. And I'm going to be back in the S block. And notice I'm going to fill both electrons in. So we're going to do 3s2. Now, how many electrons? We know that magnesium has to have 12 electrons. So we can double check to make sure that when we add all of these electrons up, we have 2 plus 2 plus 6 plus 2 is equal to 12 electrons, which is good because I needed 12 electrons. Now, sometimes that can take a while to write out, so we can use the noble gas shortcut. So neon was the noble gas that we can use. Remember the rule. Select the previous noble gas element. So I have to select a noble gas that has fewer electrons than what it is I'm trying to do the electron configuration for. So I'll write that in my brackets. And like we just saw, I'm actually going to use a different color. When we take that neon and put it in brackets, it accounts for 10 electrons. So it's going to account for all of these core electrons here. So that means the only thing that I need to include in my noble gas electron configuration is anything that comes after those 10 electrons. So I can just simply write the 3s2. So we have that listed down here as well, the electron configuration for magnesium, and then we have our noble gas electron configuration. So go ahead and try another example. Try for calcium. Go ahead and identify where calcium is on your periodic table. Yeah. What is the atomic number? Yes. So calcium has 20 protons, which means it has 20 electrons. So if we were to do the noble gas electron configuration, I would have to go and look at the noble gas that comes right before calcium. So let's write calcium into our periodic table. It comes right below magnesium. So if I want to look at the previous noble gas, I would look at argon. So if I wanted to write the noble gas electronic configuration for calcium, I would put argon in brackets. That would account for 18 electrons. I only need 2 more. Calcium is in the 4th energy level. So I'm going to write 4s2. Argon has 18 electrons. I add 2 for a total of 20 electrons. This is the noble gas electron configuration for calcium.